Today we are going to introduce the log4 shell vulnerability. But before diving into log4 shell, we first need to explain what log4j is. Log4j is a Java logging library used to write runtime information from programs to files, the console, or other destinations. It's used in many enterprise and open source applications. Then, log4 shell is a critical remote code execution vulnerability found in certain versions of log4j2. Attackers can exploit it by sending specially crafted log input. It allows unauthorized users to execute arbitrary code on the server, posing a major security threat to millions of Java applications around the world. Another reason this vulnerability is so dangerous is because it can be easily triggered just by logging a single line of user input like this command. Now, let's briefly explain how this vulnerability can be exploited. First, this is the structure of our project. Since we need to use an older version of Java and log4j2, we use Docker to define the environment for running the vulnerable application. The Docker file serves as our environment configuration file. The pom.xml is the Maven configuration file, which declares dependencies like log4j. Then, inside the source directory, we created several folders and the vulnerable app.java file. It's a simple Java application that simply logs user input using log4j, making it vulnerable to log4 shell exploits. Next, in the same directory as the Docker file, we use docker build command to build the environment. After that, we use docker run to execute the environment. When we see this prompt, it indicates that we have successfully entered the container. Then we set up a server in this container to attack the target machine. We start by creating a directory called evil server, and then create the malicious exploit.java file inside it. Typically, we might demonstrate the exploit by opening an application like the calculator, but since we are running in a Docker container, which is usually Linux-based and lacks a graphical interface, we cannot launch the calculator directly. Therefore, we choose to create a demo file called attack test in the temp directory instead. After creating exploit.java, we compile this file. Next, in the rightmost terminal, we are in the evil server directory and run this command to launch Python's built-in HTTP server module on port 8000. This allows us to serve the exploit.class file over the network so that the target machine can download it. Then, we open another terminal and enter the Docker container. Since our Docker file already includes instructions to git clone and build the JNDI exploit kit, we only need to run the final command shown here. This command starts an LDAP server on port 1389. When someone connects to it, the server returns a payload that instructs the client to download our previously hosted exploit.class file from the HTTP server. In our terminal, the exploit writes an attack test file to the temp directory, but the actual exploit simply needs to get the class downloaded and executed. The effect is the same. Once executed, the JNDI exploit kit will display several attack vectors, including an LDAP : URL, port, and a special string. This is the payload we will use in the next step. Next, in the leftmost terminal, we also enter the Docker container. Since the Docker file has already compiled and packaged vulnerable app.java, which is this file, so we can directly run the application using this command. This will launch the vulnerable app and prompt us to enter a username. At this point, we input the $, curly brackets, JNDI : and the payload we just got. As soon as log4j processes this string, it will connect to our LDAP server, fetch the exploit.class from our HTTP server, and execute it. Then the target machine will automatically create the attack test file in the temp directory. This is exactly what the attacker wants to do.
Today I want to introduce an open source framework called Tai'e that could detect past Log4j vulnerability. It is developed by two young Chinese researchers and is used to analyze Java programs. The basic idea here to detect this Log4j bug is to determine whether there is a path from Log4j's API to GNDI lookup. Now let's see how the malicious code propagates in the program. It's straightforward that the malicious code could be transferred by simple assignment. And we also see function calls could propagate the malicious code. For example, here, the function calls could transfer the taint from argument to base, from base to result, and even from argument to argument. That is to say, if we find the malicious code in the parameter of the GNDI lookup, we could say that we detect a vulnerability. Let's see how we implement this in the real code. Here it is a configure file of the analysis. First, we need to define the source. We just need a simple Java class, and we pass a special string to the Log4j API, and then we define the sink. Here it is just a GNDI's lookup function, and at the last we need to define the function which could transfer the taint, the malicious code. First, we need to define the signature of function and define how the malicious code transferred from where to where. And after we run the code, the output tells us it detects a taint flow. And we also could see the result in a graph, something like this. At the top of the graph is the source. I guess temp number 4 is the special string, and the input here is a parameter to the GNDI to the Log4j's API, and as the flow going down, at the bottom we can see it's the GNDI lookup function, and we could also find out that there are more than one path from the source to the sink. So we detect the vulnerability. That's all. We are done.